I kind of promised some. I didn't actually test this, did I? Okay, let's test this. We'll take out these comments. All right, and we'll run this again. Right, and this last one is the result of the merge sort. And you can see that we actually got this in the right order. So it's at least a good indication that we... merging is order of n in the combined size of both inputs. Sorting is order of n log n. Okay? The merge sort is... Okay. All right. So anyway, this seems to work. And we've done an analytical analysis. We've done an analytical analysis now that says how fast these things should get slow. And we've decided that insert sort is order of n squared, so it should get, every time you double the input, it should take about 4 times as long to run. And we've decided that merge sort is order of n log n. So every time you double the input, it should go slightly, if you double the input, it should take about double the time plus a little bit. Not a lot. So let's actually go in and take a look at what we have here for sorts. We talked about this last lecture. This is Lecture21 test sort.py. This imports our sorting algorithms as a module sort. Okay, and what this run in time does is it just runs our whatever algorithm we give it and times it, and then if we want, we can check to see whether it's correct or not. We'll turn that on for right now by taking this comment out. And then we talked about generate local permutations, which instead of completely randomizing our input, starts from input that's almost sorted. Okay? And all we're going to do is we're going to come in, we're going to enter a number of values, and then we're going to run all of the algorithms we have, the merge sort, Python's sort, which is, by the way, an optimized merge sort written in C. Selection sort, we talked about selection sort being a lot like insertion sort in most instances. So we would expect its behavior to be a lot like the insertion sort we have here. We wrote this one. We wrote this one. This comes with Python, and this one we wrote as well, but you didn't have to actually write it. All right, so let's kind of run this. Let's see what we get. And we'll start off with something small. We'll run it with, let's say, I don't know, 8. Right? And we're getting true that they're all correct, and 8 is so small that none of them are showing up to 4 decimal places on our timing. But it's good that we check to make sure that they're right. So let's run again. This time we'll do 16. I don't know if 16 is enough either. Nope, nothing still shows up, but they're still true. At this point, I'm going to believe that our algorithm is largely working, so I'm going to go back up here and I'm going to take off the check for correctness, just because, well, it takes time. And as we get into longer things, it doesn't take much time. It's only order of n. But we don't have to check. Once we've done a thorough check that our algorithm is correct, we don't have to do it for everything. So we'll just take that off. And now let's run. We did 8 and we did 16. Let's do 256. We're going up by powers of 2, by the way. All right, okay, now we're starting to see something. We're still not getting anything on the Python sort, but we're getting something on the merge sort, the selection sort, and the insertion sort. And as expected, insertion sort and selection sort, they're order of n squared algorithms. There's really not in the average case or in the typical case. There's really not much difference in behavior between them. So so it's kind of behaving the way we expect it to. We'll do what, 512. Right, merge sort goes from 0.003 up to 0.009. Python sort is still off the board. And these guys, selection sort's going up a little bit more slowly than insertion sort. But you can't always tell when you get down in this level. We should do this a number of times before we get there. Let's do 1024. Now we're finally starting to see our Python sort come into play. And again, there's not much difference between these two. We'll run them again. Let's get up to something big. I don't know. Let's do 100,000. Do I have flush in there? Yeah. We get up to about 100,000. Our merge sort is taking about 7.6 seconds. Selection sort hasn't ended yet. Python sort came through really fast. So as we start getting higher, this starts making a difference, right? It took us now for 100,000 values, it took me about 7.6 seconds on a merge sort. And I've been talking for more than 7.6 seconds on the selection sort. So it's taking, it starts taking substantially more time. Python sort is the built-in sort, when you're using list.sort or sorted of list. Both of those actually implement the same algorithm. One just does it in place and the other does it out of place. That's a merge sort. It's a highly optimized merge sort written in C instead of in Python. So that's why it's faster. No, Python doesn't have run end time. We wrote run end time. Okay, so it's just a little function that we wrote to do the timing. Okay, I'm going to let this run for a few minutes. I think. Maybe I'll kill it at some point. If it takes too long, we'll kill it. And now let's go back and let's try to relate this to the binary search. Okay, so we had this binary search. And I'm going to go back. I'll share this when we get back to it again. Okay, so here's our analysis of the stages for the merge sort. And by the way, this, we want you to have an understanding of what these algorithms are and the differences between order of n log n and n squared. But you'll really get into this when you get into data structures and other courses later on. This is just your introduction. You don't have to go much beyond the material we're presenting. Okay, so now let's look at a sorted list. What I had, minus 17, minus 12, 1, 2, 3, 5, 6, I don't know, 7, 9, something like that. So that's our sorted list, right? And what we saw with the binary search was that 6, 7, 8. Yeah, okay. We saw with the binary with the merge was that we did order of n work on each level, and then we had log n levels, and that got us to a sorted list. Well, if we're trying to find where a value is in the list, right? Let's say we want to find value 1.3, and we want to see where does 1.3 exist in the list, or let's do 2.3, because that gives me a beautiful breakdown. Does 2.3 exist in the list, or if it doesn't, can I figure out where it goes? Where I would insert it if I wanted to insert. So what I said was we come in here. No, that's not the, let's use 5.3. No, 2.3 should be good. Doesn't matter. 2.3 is good. So what I said was, what we do is we come in, and at each stage of the binary search, we divide the list up roughly in half, and we look at our value, and we look at this midpoint, and we say, are we on this side of the midpoint or this side of the midpoint? We divide our list approximately in half, and we say, are we on this side of the midpoint or on this side of the midpoint? And we'll use this value as kind of the determining factor. Wait. Well, actually, we're using this value as the determining factor. Okay? So we look, we see, is it this side or this side? 2.3 is a bad one because it falls right at that break. Let's say we're looking for the value 0. That'll give us a much cleaner look, just to demonstrate what we're doing. Or actually, let's do minus 15. Minus 15. There we go. Okay, so we look at minus 15. We say, does minus 15 belong here or does it belong there? And once we make that determination, then we propagate the list we're interested down, essentially. We're doing this with indices. Minus 15, minus 12, 1, 2. Right? And we divide this list up again in half. Right? And we decide, does it belong on this side or this side? Right? And again, we'll propagate this down. And we'll divide our list in half again. And now we'll say, does it belong on this side or this side? And we'll propagate it down again. And now, at this point, it has to either be here or belong here. And we can make that decision. Okay, and the key is that this comparison, this decision, takes essentially one step, or at least a small constant number of steps to make the decision. We have to calculate the midpoint, and we have to do a comparison. Right, so this takes order of 1. That's constant. Right, to get from here to here takes order of 1 constant. To get from here to here takes order of 1 constant. To get from here to here takes order of 1 or constant time. If we look at the number of levels again, right? We make one transition, 2 transitions, 3 transitions. So again, for a list of length 8, we make 3 transitions. If we started out with a list of length 4, we would just have 2 transitions. If we started out with a list of length 16, we would have 4 transitions, right? So again, this getting rid of half the information is order of log n behavior. Only this time, moving from stage to stage can be done in a constant number, a very small number of operations, just basically calculating the midpoint and choosing a side. So now instead of order of n times order of log n, we have order of 1 times log n, and that's just order of log n. So this is kind of the reverse of the merge sort. Merge sort, we start out with lists of length 1 and we synthesize together until we get to the bigger list. And there's more work on each level, but overall the structure is the same. Both allow us to do about half the work, or allow us to do, half the work. Allow us to either double the size of the list or halve the size of the list in one stage. All right. Any questions here?
Question?
Yeah, go ahead.
So yeah, the list has -17, -12, 1, and 2, and you split it from the other part, and then it turns into a 15.
That's just because.
So you're just doing the reverse of what you did before.
Essentially, yeah. Except the effort to get between stages is much less. But yeah, it's essentially doing the reverse of what we did before. Okay.
Okay.
Sorry about that. That minus. I didn't think I picked the end point number, but it worked out well for me, so I was just going with it. All right. Okay. So that's kind of what we wanted to talk about, sorting, and selection sort still hasn't finished. Now my machine is a little overburdened because of doing this recording and everything else. So it shouldn't take this long. But let's kill that. Let's run it one more time. This time instead of 100,000, we'll use 10,000. And hopefully this will not take forever. Maybe I should start building this up. Let's try 5,000. Or 1,000. We did that, okay. 1,000 under a second. 2,000. We're starting to see Python merge sort come in here. Selection sort, insertion sort both take about 2 seconds. We'll go 4,000, and that may be as far as we're going to go today with these two. Because then I want to show you something else. Okay, so you can see that these guys went from 2 to about 7 or so, right? 4 or 5 times, 2 to about 7 or so, about 3 times as slow. That's not bad, actually. But yeah, they're getting slow much faster than these guys are getting slow. And the Python sort, by the way, so again, this sort and this sort are essentially the same algorithm. The difference here is difference between running in Python and the difference in running in C. This Python sort actually is a C routine, highly optimized, compiled, runs much faster than an interpreted language. But it's essentially the same algorithm. So they should be going up about the same amount. These guys just are in a different playing field. Okay, I want to show you one more thing. We talked about this generate local perm. And I said that in general, insertion sort and selection sort behave the same. Insertion sort creates a hole. When you're inserting the second element, it creates a hole in the second position of your list. And then it moves that hole down till it gets to the point where the element you're currently looking at, the element that was at the hole position, can be inserted. Selection sort, the first time through, you grab the smallest object. The second time through, you grab the second smallest object. And you just keep grabbing objects every time. So you always have to go all the way down to the end of the list. And then to make sure that you've grabbed the correct element. So your list is continually being incrementally sorted. But every time through, you're traveling to the end of the list. And that's the same behavior as the insertion sort when you have to move that hole all the way down. But it turns out that they behave very differently if you have something that's almost sorted. So if you look at generate local permutation, like I said last week, this essentially takes our sorted list, right? We start out with our sorted list. It essentially takes our sorted list and just permutes it a little bit. So things are just a little bit out of place. So let's put that in instead of this random shuffle. Right, so we'll do that. We'll take the random shuffle out. And now let's run this. I think the last thing I ran it on was 4,000, right? And selection sort took 6.8 and insertion sort took 7.3. Selection sort should still take about 4.8 or 6 seconds. But now look at our insertion sort. Our insertion sort is now faster than our merge sort. And it turns out that that's because now we've broken the rule on how far that hole has to travel. Now, because we're using this generate local perm, instead of traveling on average the length of the list, it's on average traveling 10 spaces, right? This 10 represents our max shift. So on average, it's traveling less than 10 spaces to get to, the hole's traveling less than 10 spaces to get to its final resting place, on average. So what we see here is that if that reduces the cost from order of n to insert, to move the hole to the correct position to this constant. And when we do that, now all of a sudden we get a completely different behavior on the insertion sort. Instead of being an order of n squared algorithm, it's now an order of n algorithm. Okay, so it's just this is a if you know your input is almost sorted, things are almost in the right place, then the insertion sort's really very fast. But in a random vector, it's order of n squared because we don't know how long that hole is going to have to move. So it doesn't, when we're doing these bounds analysis, you have to think about, are there special cases where even an inefficient algorithm works very well? I'm going to take out selection sort for a second because I want to run this on we'll run this on 100,000. We'll start out with 10,000, right? And we'll see that, right, merge sort takes about 1/4 of a second. Python sort takes, 1/1000th of a second. But the insertion sort is only at, 8/100ths of a second. So it's not all that slow. And we can run this again, and now we can get very good results up to even 100,000. I hope. Merge sort takes, let's see, I would expect, didn't give me a chance to expect, it just did it. All right, so this is just experimental. This is how you would go in and test your code experimentally to see what the behavior was. And if you actually wanted to test this, you would run this like 10 times, on a machine that doesn't have anything else going on. You would run it 10 times with the same values or something like that, or 100 times with the same values. And you would calculate the average of those runs. So merge sort's coming out at a little over 3 seconds for 100,000 values. Python sort's coming out 0.17. That's staying pretty stable. Insertion sort about 0.6, 0.7, or 0.7, 0.8. Okay, so you could actually generate these and plot them, and then look at the shape of the curve to figure out. And the other reason we study these is these are really good ways. These are very important problems in computer science. And this isn't always about getting things to run fast. In general, I would not expect you to write your own sort routine. If you had to, in a pinch, you should be able to do it. But we study these to study, algorithms that have particular behaviors, or how we can make our behaviors better. I used most of this lecture talking about things that I wanted to talk about. I kind of was afraid that's where we would go with this. But I think we've done a good job of hitting up some very complicated topics with sorting and merging and searching. So